We're live. Welcome to AP Calculus AB. Let's get started. The homework that's due on block day, just so you know, can be found right on the website. So let's take a look at where to find the homework that's due block day. Now, when you get to the website, it'll look something like this. And all I ask you to do to find the homework is click on Topics, Pre-Calculus Review, and the homework is on the Problem Set 4 link. And if you click on Problem Set 4, the only problem I want you to do for homework is problem 6. It's a multi-part problem. And we'll probably do enough in class today for you to understand parts A, B, C, D, and E. We probably will not get to relative growth rate. So if you want to try problem 6F, I mean, you can, that's fine, but my guess is that we'll just do that in class on block day. So the homework that's due on block day is from the Unit 4, that's Unit 4 of pre-calculus. Unit 4, problem set. Problem number 6, parts A through E, is what it will likely be. So here we go. Let's find out what's going on. We've had this pattern in Unit 0. We're in Unit 0, the pre-calculus review unit, of learning using paper notes. If you want a sheet of paper, feel free to grab what you need. And let's begin the warm-up question. Here we go. Yeah. Here is the warm-up example, problem 1. A population of 75 million people doubles every 3 years. So, suppose we let T represent time and P represent the population at year T. Suppose at time 0, the population is 75 million. Population is measured in millions. And every 3 years, the population doubles. So we're after 3 years later, we're up to 150 million and keeps going. At 6 years, we're up to 300 million. Would you please write a model for the population as a function of time? An algebraic model. So basically what I want you to do now is write an equation for P as a function of time. You may begin. I'm going to pause the camera, then we'll come back. And welcome back. Okay, you've had a chance to work on this. And would you tell me, please, Shiara, what equation did you come up with for this?
I have P equals 75 times 2 to the T over 3.
P equals 75 times 2 to the T over 3 power. Now, this is actually correct, and this is probably the fastest, or there's other ways to do it, like you could use the PERT formula to express the answer here. However, this is what I was hoping for. I was hoping that you would recognize that in an exponential function, you start out somewhere. You have a starting point, in this case, 75 million people. In an exponential function, you always multiply by something every so often. In this case, we're multiplying by 2 every 3 years. And you may have never looked at exponential functions in such an elegant fashion before, but exponential functions are written in the form a times b to the variable. Now, if you were to put a third one in there, a was 75, b was 2, and c was 3. In any exponential function, you start somewhere and you multiply by something every so often. And when I teach Algebra 2, I like to draw a contrast between a, b, and c in an exponential function and a linear function. So there's a few things I'd like you to say. I'd like you to say, well, I'll tell you a story first. The author of our textbook, Ron Larson, teamed up with Tim Canel, who was my boss up at Stevenson High School, where I worked for 29 years. So one evening, Ron invited me and my wife out to dinner. He wanted to invite me into a project of writing graphing calculator activities for their new project. I mean, he does college calculus books, but they were trying to move into the high school market to do Algebra 1, Algebra 2. So yeah, I was happy to go to dinner, and he invited me to write some graphing calculator activities for algebra classes. And from Ron Larson, I learned that linear functions and exponential functions are actually quite similar. Dr. Larson taught me that in a linear function, you start somewhere and you add something every so often. Like you could start at 75 million people and you could add 10 million people every 3 years. If I had said, we're going to start at 75 million people and we're going to add 10 million people every 3 years, then we would have said, instead of, the slope, rise over run, is 10/3. And using the y equals mx plus b approach, we could say, yeah, the slope is 10/3. But notice that Chiara, it is Chiara, right?
Chia.
She or chi?
Chi.
Chi. Chiara? Chiara, is that it?
Yes.
Oh, okay. Thank you for helping with that. So Chiara had that t over 3 in there. There's actually, there's a t over 3, in this case x over 3, in both linear and exponential models. And that's what was eyebrow raising in what I learned from Dr. Larson. It's like, okay, you could start at 75 and add 10 million every 3 years, or in an exponential function, we start somewhere and we multiply by something every so often. That multiply by something every so often is what led Jack to be thinking in terms of geometric sequences. So that's a very good thought, nice connection there. So when I say go, I'd like you to, oh, by the way the question is worded, we start at 75 million and we multiply by 2 every 3 years. So instead of starting 75 and adding 10 million people every 3 years, we're starting at 75 million people, we're multiplying by 2, doubling, every 3 years. So here's what I'd like you to say out loud and in unison. I would like you to say, in a linear function, we start somewhere and we add something every so often. But in an exponential function, we start somewhere and we multiply by something every so often. They're very similar, just a little bit different. In one, you add something every so often, the other, you multiply by something every so often. Let's see how this goes. Ready? Go. In a linear function, you start somewhere
and add something every so often.
In an exponential function, you
start somewhere and then multiply something every so often.
Thank you for letting them hear you on the World Wide Web. Yeah. Start somewhere, add something every so often. Graphically, that would be, you start at the intercept, in this case the y-intercept, and you add 10 million people every 3 years, the slope is 10 over 3. In an exponential function, we're still starting at 75 million people, and it doubles. Now, both of these curves contain, actually, there's a way to make an even better connection, because just using T and P, if we did 0, 75, and 3, 150, we could come up with both the linear model. The linear model would be, if I said we add 75 million people every 3 years, you would have said, well, we start at 75 and we add 75 million people every 3 years, which is really 25 million people per year. That's the rise, that's the run. The slope is 75/3. But I'm writing the slope a little bit differently. Rise over run, instead of pointing the rise over run out front, I'm just trying to illustrate how connected linear functions are to exponential functions. If it were an exponential function, we'd say we start at 75 and we double every 3 years. Graphically, one of them, they both have an intercept. These both start at the same place. And they both contain the point 3, 150. Just that one has it's a linear function, the other is an exponential function. So exponential starts out behind linear, but then it catches up and surpasses, goes super fast. So we're going to use some building blocks to reinforce the contrast between a linear function and an exponential function. I have the building blocks for you in a Ziploc bag. I'm going to hand them out to you now. Let's pause the camera. Hi. Here's what I'd like you to do with the Ziploc bag. These are the building blocks. We're going to have a little relay race, even though it's cross country. It's not track season yet. It's still cross country. We're going to do a relay race. The first person on your team, you have a team of 3 or 4 people, and one of the teams is going to be selected to come up here to the board. Here's what you're going to do when you get to the board. The first person in the relay is going to say in a linear function, output, that's like, y or population. Output equals, and then we have to start somewhere. We're going to start at the initial output. It's like starting at 75 million people. So output equals initial output plus, go ahead and arrange your blocks like this. Take the blocks and arrange them so that they say output equals initial output plus output change. Output change is just like y2 minus y1 times input over input change. Here you do not use the output ratio, use output change. And you would, like suppose we started 24 million people, and every 5 years we lose 6 million people. In a linear function, you can write it like this. Notice how I rewrote the slope. This is a sneaky move I made. Instead of writing slope, output change is rise, input change means subtraction. Input change is run, so rise over run. But notice how I broke the slope up? Instead of rise over run, I'm putting the run over here so that I can later show how similar linear functions are to exponential functions. So, we start somewhere and we add something every so often. Let's try this together. When I say go, I'd like you to say out loud and in unison. I'd like you to say, in a linear function, output equals initial output plus output change times input over input change. Let's try that one. Ready? Go. In a linear function, output equals initial output plus
output change
times input over
input
change. So if you have those building blocks in your mind, then you can see they're all right here. The input change was 5. 5 years, we went down 6 million people. So you could say in this population, we start somewhere, 24, and we add -6 every 5 years. Output, why is the output? The initial output is, hello, okay, so the initial output is 24, and we add -6 every 5 years. Let's make that a +5. So that would be the linear model. What if we wanted to create an exponential model? Instead of adding -6 every 5 years, what if the population drops by 25% every 5 years? The OR stands for output ratio. Ratio implies division, and this smooth bar implies that I divided 18 by 24. What if we have a population that decreases 25% every 5 years? How would we model that? We would model that with an exponential function. So the next thing we want to arrange with our building blocks is this. We want to be able to say in an exponential function, the output, so that we can model this situation, a drop of 25% every 5 years. Okay, so for an exponential function, output equals initial output times output ratio to the input over input change. You see, it's almost the same building blocks, but using that we could say output equals initial output times the output ratio. The ratio of outputs, 18 divided by 24 is 0.75 to the x over 5. So ratio implies division, change implies subtraction. So when I say go, I'd like all of you to say out loud and in unison, output equals initial output times output ratio to the input over input change. Let's try it. Ready? Go. Output equals times to the,
Input over input change.
yeah, so here's how the relay race goes. It'll be on the clock. And so let me open up the clock. And you have the building blocks on your desk because I want you to practice racing before your group comes to the board. Okay? You need to practice with the building blocks at your seat. This will be kind of fun. The clock will be set to count up. It'll start at 1 second. And so if you're in the relay race, if you're selected for today's performance, then, and if you're the first person to have the baton, which is really a stylus, what you will do is you will press play to start the clock, because we're going to time this. So we'll press play, and then you will say, you'll be up here in front of the room talking. You'll say, in a linear function, I'm actually going to have that selected like this. You're going to say, in a linear function, output equals initial output plus output change, like the rise, times input over input change, and then you'll hand the baton to the second person in your group. The first thing that person will do, the second person in the relay will press the next button, and that will enable them to go to the exponential function. And that second person will say, in an exponential function, output equals initial output times output ratio to the input over input change. They both have input over input change. Hand the baton next. The third person in the relay says, in a linear function, output equals initial output plus output change times input over input change. It's good exercise, really. The fourth person, if there is not a fourth person, then the first person has to go twice. So then the first person or the fourth person will click next and go back to exponential functions, and you will say, in an exponential function, output equals initial output times output ratio to the input over input change. If you're the fourth person across the finish line, you have to click, and then you'll have your time. Subtracting 1 second from that, we'll say, your team got 1 minute, 31 seconds. Yes?
You have to say that out loud while you're doing it? Or you just do it?
The part about, and the fourth person has to click that button.
No, like you have to say output equals.
Yeah, you have to speak as you're doing it, yeah. Because the idea is to put the V in vegans round, to be verbal about this, okay? To be verbal. So would all of you please practice the relay? I'm going to hit the camera here. Enter to the next person, who first thing you do is you click next, and then keep going. Start with exponential. So I know, so you have to change the name.
Okay. Exponential function is output equals initial output times output ratio over
So to
the input over input change.
pass the baton. Click next.
So linear function is output equals initial output plus output change times input over input change.
Now for the anchor leg. And just use the other side of the stylus.
Oh. So the exponential function is output equals to initial output times output ratio to the input to the input change.
1 minute and 43 seconds. Let's give them a hand.
We got next one. We're up for the challenge.
Now, on block day, we'll see if any of you can beat that. For now, we have to do a few examples of what's on the homework. So, let's let's take a look at this situation. Good job, guys. Eyes up front. Here we go. Let's continue. Suppose we have another population, and we start at 50 people, and let's say the half-life is 6 years, which is another way of saying it decreases by 50% every 6 years. Let's look at the output ratio. The output ratio is 1/2. So we could say that output equals initial output times output ratio to the input over input change. Whenever you have a half-life model, the input change is the half-life. Now, I could ask you questions like, what is the percent decrease per 6 years? And you would probably look at that and say, oh, no big deal. It's clearly dropping by 50% every 6 years. But sometimes they're actually, that percent decrease per blank years. I just want to rewind a little bit to our first example where we had P equals 75 times 2 to the T over 3. What was the percent increase on that problem? What was the percent increase per 2 years? Can someone tell me by what percent was the population per 3 years? By what percent was the population increasing every 3 years in our opener example? Now, I'll be honest with you, some people look at that and they say 100%, some will say 200%, some will say something else. What do you think it is? What is the percent increase per every 3 years? Go ahead, Crystal.
200.
Okay, raise your hand if you agree with that's a 200% increase every 3 years. Okay, so about half the class has their hands up. It's actually 100%. It's all, because think about it. If you're doubling every 3 years, take your age. Suppose you're 18 years old. If your age doubles, it goes from 18 to 36. It goes up by 100%. When you double, you go up by 100%. If you want to find the percent change, class, always take the output ratio, whatever the output ratio is. Take the output ratio minus 1 times 100. So 2 minus 1 is 1 times 100, and then tack on a percent. That's 100% increase. So if the output ratio is 3, just a quick side example on that, what if I said, the population is 75 and it quadruples every 3 years? What percent is it going up by every 3 years? 300%, because you take the output ratio minus 1 times 100, tack on the percent. So back to our question. What is look at that. Output ratio minus 1, that's negative 1/2, times 100%. It's decreasing by 50% per year. How about per 6 years? Now let's change it to a 1-year model. What is the percent decrease per year? Now, most pre-calculus students, when they hit this, they say, well, if it's 50% every 6 years, let's just divide by 6. It's whatever 50 divided by 6 is per year. How many of you are willing to admit that even though that's incorrect, that's where your mind tends to go? You're thinking, well, if we're going down 50% every 6 years, that's probably 8.3 repeating percent that we're going down per year. Is there anyone willing to admit that your mind tends to go there? Yeah, okay, thank you for admitting that. We won't say what your names are, but yeah, that's super common. See, what the correct way to do it is not to divide 50 by 6. The voice inside says that, but your voice inside thought that 0.9 repeating was equal to 1, or was less than 1. Here's what you do instead. You have to change the 6-year model into a 1-year model, because I didn't say per 6 years. So it's just an algebraic thing. Let's get in. See, this is what we call the 6-year output ratio. We want to manipulate algebraically this equation to change it from a 6-year output ratio to a 1-year output ratio. And here's how we do it algebraically. Let's take our 50 times 1/2 to the T over 6 and basically use an algebra 1 skill, make it 1/2 to the 1/6 power to the t over 1. Now it's output equals initial output times output ratio. Now the output ratio is 1/2 to the 1/6 power to the input over input change. Since the input change is 1 year, we call 1/2 to the 1/6 power a 1 year output ratio. So we'll take that 1 year output ratio, subtract 1, and multiply by 100. That can easily be done on the calculator. Notice it's not 8.3% per year that the population is sinking. It is 1/2 caret 1/6. It's actually minus 1 times 100. The population is actually going down 10.91% per year. So let's see if that really makes sense. I mean, does it really take us down to exactly 1/2? There's a stunning demonstration of this that we can do in the minute that remains. I'm going to take the output ratio of 1/2 to the caret 1/6 power. I'm going to store that in O for output ratio. Now watch this. I'm going to take 50, enter. I'm going to multiply it by the output ratio, alpha O. 1 time 2, 3, 4, 5, 6. 6 years took it down to exactly 25. So it really is not going down 8.3, it's going down, take that output ratio, subtract 1, multiply by 100. The answer is 10.91% per year. When the population is decreasing 50% every 6 years, it's going down 10.91% per year. 10.91%. Now, the homework, it's just parts not A through F, but it's Unit 4 problem set. Problem 6, do problems A through E. A through E. So Unit 4, problem 6, A through E is due on block day. You are dismissed.